Hello, everyone. Welcome to the 82nd online Spintronics seminar. Today, we welcome Professor Igor Barsukov to give us a talk. And he's a JET distinguished faculty at the University of California, Riverside. He studied physics at University of Bochum, Germany, where he developed magnetodynamic microscopy techniques. As a recipient of the Marie Curie Fellowship, he then worked on magnetic core shell nanoparticles at the Academy of Sciences of Czech Republic in Prague. He holds PhD in physics in 2012 from the University of Duisburg, Essen, Germany, where he investigated magnetism structure correlations using MBE and ferromagnetic resonance spectroscopy. As a postdoc, he moved to University of California, Irvine, where he worked on nonlinear magnetodynamics and interfacial spin torques in collaboration with Spintronics industry. Since 2016, his research group at UCR's Department of Physics and Astronomy designs spintronic applications and investigates spin dynamics in nanoscale systems using microwave terahertz spectroscopy, magnetotransport, and computational methods. He's executive committee member of the magnetic division of the American Vacuum Society and co-chair and organizer of the upcoming 7th workshop of Magnonics in 2022. So without further ado, Professor Barsukov, please go ahead with the talk.
Thank you very much. Thank you very much for the introduction. Hello, everyone. Thank you for joining to listen to my talk, whatever your time zone is. Shin, thank you very much for mentioning the workshop. If I may take just 1 minute to briefly announce it before I start with physics. So indeed, in the summer of the next year, so at the end of August and beginning of September, we are very happy to announce an in-person conference. This is the 7th workshop in the series of workshops on magnonics. It will take in Southern California. So we are working right now on the exact location, but most certainly it will be somewhere very near the beach. And this is the best season to visit California, I would say. So we are very excited. Ilya and I, we are working on organization. You see here a very prominent team of the Scientific Advisory Committee. So I'm certain that thanks to the effort of the Scientific Advisory Committee, this will be a very exciting program of invited talks and tutorials. But the conference is also open for contributed talks. So please keep in mind this date, the end of February. So basically the beginning of the next calendar year, the conference will go into the abstract submission. Please pay attention if you're interested. I hope to see you all there. The website is magnonics.us. Okay, so with this, let me go to the physics of my talk. So I'm going to talk today about the interplay of spin torque and nonlinearity, disentangling and controlling magnon processes in nanomagnets. So let me very briefly maybe motivate my talk. So this concerns with nonlinear spin dynamics in nanomagnets and just why would we work on nonlinear spin dynamics. First, because it is a very exciting field of fundamental physics and it has many parallels to other subfields of physics, in particular nanomechanical system and optical system. And by learning more and more about nonlinear physics and by looking at this parallels to other subfields, we actually can extract new ideas for example, new applications, new technologies for our spintronics. Besides these fundamental aspects of the physics that I would like to present, there is a very straightforward applicational aspect. And to boil it down, to summarize it, it is that nanomagnets are the building blocks of many spintronic technologies. And therefore, understanding spin dynamics of nanomagnets is really crucial for the advancement of applications. However, in nanomagnets, many aspects of dissipation and spin torque response actually have remained rather elusive, not fully understood. And I'm going to show you a couple of examples on the other slides. Okay, so the devices that I'm going to focus in my talk are the nanoscale magnetic tunnel junctions. And the reason for this, so why we use this particular sample system, is the following. So first of all, these devices are the flagship technology of Spintronics, if I may say. So these are constituents of the spin torque memory that already made the leap towards commercialization. They are used as very sensitive magnetic field sensors and microwave sensors. They are the basis of many spin torque oscillators. And as such, for example, they have been shown to be useful in the context of neuromorphic computing. And also rather recently, it has been shown that small MTJs with small magnetic anisotropy can be used for probabilistic computing. So you see the applicational relevance is huge. So let me very briefly recap what a typical magnetic tunnel junction looks like. So this is a multi-layer device consisting of the layers that are shown here. So let me start from the bottom. So on the bottom, we have a synthetic antiferromagnet. So we have here two ferromagnetic metallic layers that are separated by a non-magnetic interlay. In this case, this is ruthenium. By means of RKKY interaction, the two layers are magnetically coupled. They are coupled such that their magnetization align itself antiferromagnetically to each other. The bottom layer of the SAF is exchange biased to an underlying antiferromagnet that is not shown here. So the underlying magnet is set in one particular direction. This leads also to the pinning of the magnetization of the SAF top layer. So this layer basically becomes a pinned layer, a reference layer. Now the SAF top layer is separated from another ferromagnetic layer here by a tunneling barrier. In this case, in our case, this is MgO. And there is a rather small interaction, exchange interaction through MgO. Thus, the free layer here, so this top layer, is indeed free in the sense that magnetization can more easily rotate, can be aligned up and down. So you see here, this is, for example, as I mentioned, the constituent of the spin torque memory. So by orienting magnetization of the free layer up or down, you can encode information. Now, more importantly, and this is the main functionality of this device, is that because of this tunneling layer, you can achieve a very high magnetoresistance. So this is the tunneling magnetoresistance. Just by letting through the electrons of very particular symmetry, you can achieve really high magnetoresistance ratios. You can read out really huge electrical signals depending on the orientation of magnetization in the free layer, and you can also achieve great spin polarized electrical currents. So now, after recapping what a typical MTJ looks like, I want to go to the fundamental physics aspect of it, and this is that we are going to use these magnetic tunnel junctions as sample platform for studying individual zero-dimensional magnets. So the MTJ nanopillars, so these nanoscale devices that I'm going to use, have typical dimensions of the thickness of the layers in the range of 1 nanometer, and lateral dimensions will be in the range of few tens of nanometers, maybe 100, 150 nanometers. So if you think about the spin waves, about the low frequency range of the spin wave spectrum, you will find that the spin wave spectrum will be fully quantized. So in this sense, this magnetic system, this free layer that we're going to study, can be considered zero-dimensional. Okay, so now, as I mentioned, the key functionality of many Spintronics technologies is the spin torque. So this is the competition or the ability to change the effective dissipation of the system by a spin torque. So, and in order just to do this, we first need to understand what is the dissipation in such a nanoparticle. So if you think of extended systems, like for example, if you just take a ferromagnetic thin film and you would measure dissipation, magnetic dissipation as a function of frequency of magnon modes, you will typically find something that behaves like this, basically a straight line, right? So this will be a Gilbert damping or Gilbert-like damping with the slope of this line corresponding to the dissipation rate. However, if you go to a typical nanomagnet, and this is indeed the data from a typical MTJ device, you will find, well, a mass that looks like this. Okay, so this definitely behaves not Gilbert-like, and it is extremely difficult to extract the dissipation from such a measurement, and even though more complicated to understand how to operate such a device with a spin torque, how to fight against this dissipation, even though the dissipation is not understood. So this brings me to the outline of my talk. After this motivation, I would like to talk about the constituents of this anomalous dissipation in nanomagnets. Then I would like to speak about how this nonlinearity, how this nonlinear dissipation present in nanosystems interplays with the spin torque. After this, I'm going to talk about the possibilities how to control this nonlinearity, and then I will try to summarize different types of nonlinearities in nanomagnets. The list may not be exhaustive, but I will do my best. Okay, so let us go back to one single MTJ device. So this particular one has a lateral dimensions of approximately 100 nanometer, and the ferromagnetic layers, in this case, this is iron, cobalt, boron compounds, rather thin, and they have rather strong perpendicular magnetic anisotropy, such that magnetization of all these layers is perpendicular. So that means this layer shows down, this layer shows up, and this layer can be switched up or down. Okay, so now using this one single magnetic tunnel junction nanopillar, we can measure the microwave, we can perform microwave spectroscopy using the field modulated spin torque ferromagnetic resonance. So although the system is very small, we can get very accurate signals and see multiple excitations. So, and if we look at this with magnetic field applied along the easy axis, in this case perpendicular to the sample plane, we will find that there are three very well pronounced excitations that with the frequencies of these increasing linearly with applied magnetic field. So what we can do then is we carry out micromagnetic simulations of this device. So in these micromagnetic simulations, we include the entire multi-layer stack. So not just the free layer, but also the underlying layers, because we want to understand whether the spectrum that we observe here in experiment has something to do only with the free layer or other layers also contribute. So the bottom line is that for the devices that we study here, the interaction of the free layer and the underlying layer is very small, such that all the excitations that we observe in our experiment are indeed located, hosted only in the free layer. And by doing these micromagnetic simulations, we can conclude that these excitations are simply spin waves of the free layer. And because in our case, the shape of the free layer is a elliptical disk, these spin wave modes are simply just the normal modes of an ellipse. So we start with the lowest energy, it's just a quasi-uniform mode. If you go higher in energy, you will get one excitation mode, then another one 90 degree to it. And if you go higher and higher, you will have an increased number of the excitation nodes. So in this case, I'm labeling this magnon modes as 0, 0, 0, 1, 1, 0, basically saying how many nodes a particular spin wave has, but later I will just forgo this notation and just say first, second, third, etc. I will just count them up. Okay, now if we look at this measurement here, we immediately see that there are anomalies in the spectrum. So first you see that the lowest energy magnon mode has a splitting here at this particular field, and then there is some broadening here. Then we see something here that looks like an anti-crossing, and which is very peculiar because typically for an anti-crossing, you would expect that there are two modes or some modes of anything, let's say, right, and go into interaction that just cross in frequency. However, you can see here, there is actually no modes. So we do not expect any magnon modes in this region to be with this law. Nonetheless, we see a clear signature of an anti-crossing. So we can discuss this later. And there is an additional, if you look at the right angle, there is one anomaly here. Okay, so when we look at these anomalies, we should look at the frequencies and fields at which these anomalies occur, which will allow us to actually find an idea what these anomalies are. And if we look for one particular field, for example, this field H1, we'll see that the anomaly occurring of the lowest energy mode and this anomaly occur basically at the same field. And the frequencies of the eigenmodes are such that this frequency here is exactly half of the frequency of the higher order mode. If you go a little bit higher in field, so you go to another characteristic field at which anomalies occur again. So we see anomaly here. And if we go twice this frequency, we will arrive at the next higher magnon mode, and we will see an anomaly here as well. So just by comparing the frequencies, we can already assume what kind of process, nonlinear process, will be responsible for this. And this is such a process where two magnons of the lower energy mode transmutate into one magnon of the higher order mode. Okay, so one more time, this is a nanomagnet. So these modes are completely localized, right? So we don't need to worry about the translational momentum. The only thing that we need to worry about is the conservation of energy, right? So if the energy of these two modes together is equal to the energy of the higher order mode, we can have this process. And of course, we can have the inverse process. So just to say the official term of this process is the degenerate resonant three-magnon process. So three-magnon because there are three magnons that are involved in this process, degenerate because there are two same magnons that participate here, and resonant is because it takes place near the magnetic field where the energy conservation is fulfilled. Okay, so now if we look at the dissipation of this lowest energy mode, so this is of particular importance because the lowest energy mode is determining many technological aspects of devices, we will see that the line width, which is FMR line width, which corresponds to dissipation, indeed shows two very well-pronounced anomalies, and these anomalies pretty much occur, well, where we already by eye see these anomalies to occur. So we definitely see that the dissipation shows anomalies, and these anomalies are likely to correspond to the three-magnon scattering that we have observed. So let us, well, set up a theoretical model and see whether we can handle this three-magnon process. So in the most simple approach, we define the two modes. So this is the H bar is 1. So we make this as, we simplify this. So we look at the lowest energy mode, then we look at the higher order spin wave mode. Then we introduce a mode coupling. So we say two magnons of the lower mode go into one magnon of the higher order mode, and of course the inverse process. And then we add the external drive. In addition, we define the dissipation function. So this is just the Gilbert damping, the intrinsic damping of the mode of the lowest energy mode and of the higher order mode. Now, for those of you who work with nonlinearities, I want to say that we also added the so-called intrinsic nonlinearity. So this is the effective nonlinearity, phenomenological nonlinearity often introduced in the system. So this would correspond to just phenomenological nonlinear frequency shift, and this would correspond to nonlinear damping. I'm going to talk about it in a moment. Okay, so let us take a look at this Hamiltonian dissipation function. We can set up equations of motions, and we can solve these equations of motions numerically, in some cases, limiting cases, even analytically. And from this solution, we will find this A, which basically corresponds to the amplitude of the magnon mode. And this is exactly what we measure in experiment. So we can compare this directly. So you see here the experiment. You see here the spin torque ferromagnetic resonance. The response of the device is a function of frequency. And what we do is we increase the excitation amplitude. So if you increase the excitation amplitude, the amplitude of the mode here that you see the magnon mode increases. And this is the corresponding simulation. So for this particular measurement, we set the external magnetic field such that we are outside of the three-magnon regime. So we set the magnetic field somewhere far away from the crossing of the twice the frequency of the lower mode and the frequency of the higher. Okay, so we try to stay away from the trouble. Okay, what we observe if we go to really high excitation amplitudes is, well, something that is not very surprising. This is just the foldover, right? So the standard nonlinearity that you would typically observe. However, now if you go to the three-magnon regime, so if you set the magnetic field onto this characteristic field or really close to it, you will see that with increasing excitation amplitude, the normal-looking excitation starts to, the line starts basically to split. And we can follow this in the simulation based on our Hamiltonian, and we indeed see that we observe the splitting of the line, and we see in addition even more some fold over, and this fold over is rather unusual. Typically, you would expect the fold over to be only towards one side, either to the left or to the right. In this case, we see for the split peak always that this fold over goes to both directions, to the left and to the right. Okay, so this is very unusual, and I'm not sure if anything like this actually existed in extended systems. In nanomagnets, we have found this very peculiar anomaly of the spectral shape. Now, again, I just want to be complete and say that yes, we have included this phenomenological nonlinearity, such as the phenomenological nonlinear frequency shift and nonlinear damping. We ran simulations. Here you see the red line is the simulation where all the intrinsic nonlinearities are set to 0, and the blue one is such simulation where one of these parameters is set to some higher value. And you basically see that whatever intrinsic nonlinearity you choose, it is only the 3-magnon process that leads to observed anomalies, and even more, the intrinsic nonlinearities that are typically introduced in the system play a rather secondary role. Okay, so as I mentioned, we can simulate the magnitude of the magnon mode. From this, we can literally just simulate the whole spectrum. We can extract the line widths, and we can compare this directly to our experiment. And so we did, and you can see here the red line is the simulation based on the Hamiltonian that I have shown to you. And we see an excellent agreement with the theoretical model. So in this fitting procedure, or in this rather simulation procedure, actually, we see that indeed there is a resonant enhancement of the dissipation that is parameterized by the magnon coupling strength. So of course, in order for the 3-magnon scattering to occur, you need the frequencies of the magnon modes to be in match. But even more, you need this phenomenological coupling that basically says how strongly are the magnons coupled to each other. Now, very importantly, and this is perhaps indeed different from the nonlinear spin dynamics in many extended systems, is that this nonlinearity that we have observed is prominent even at low excitation fields. So typically, if you would work with extended systems, if you want to get rid of nonlinearity, you would just decrease the excitation level, right? And then you will get a very nice performing system. Well, in these nano devices, very often what happens, if you want to do this, you decrease the excitation level to the point where you basically cannot see anything. So here, this nonlinearity is very strongly pronounced. And in particular, this 3-magnon process that I'm talking about right now has no threshold. So it is present there all the time. There is no threshold for it. And in many devices, indeed, we see that this nonlinearity that we have observed is indeed the dominant dissipation channel. So this basically dominates the dissipation of the system. All right, so now let us take a look how this nonlinear dissipation interplays with the spin torque. As I mentioned, this is the key functionality of many Spintronics technologies, so this is very important. So let me very briefly summarize again what the spin torque is and how it affects the magnetization. This is the very crude model, so I assume here the macro spin approximation. This is the Landau-Lifshitz equation, Landau-Lifshitz-Hilbert equation with the added Slanzewski torque. Okay, so this is a spin current that we inject into our free layer. The sigma is the polarization of the spin current. This is the magnitude of the spin current, and there is some phenomenological constant that takes into account all the prefactors. Okay, so if the spin current polarization is parallel to the equilibrium direction of magnetization, what will happen is that the incoming spin current will renormalize the effective damping of the device. So the damping will go down, you will have an anti-damping spin torque, and there will be 3 possible scenarios. So first of all, you can just have precession of magnetization with a modified damping. If you send a rather strong pulse of the spin current, you can have a switching. So this is what happens in the spin torque memory. Or if you send a critical or slightly supercritical spin current into the system at moderate levels, then you can have an auto oscillation. So this term basically will just negate this term. The damping will effectively go to 0. Magnetization will destabilize and go into persistent oscillations. And This is how the spin torque oscillators work. So in our experiment to perform systematic studies, let us focus on the damping modification. So we will just send electrical currents through the MTJ, and we will measure the dissipation as a function of the spin current. Okay, if we do that, let us start again first with the stay away from the trouble. So let us choose a magnetic field for which the 3-magnon process is far away. Okay, and then we measure the line width, we measure the dissipation of the lowest energy mode as a function of the spin current. So here for the negative spin current, the spin torque acts as a damping enhancing, and for the positive current here, the spin torque is anti-damping, so it reduces the effective damping. And indeed what we see is that the dissipation decreases linearly with the electrical current sent through the device. Only when you come to the critical regime, so very, very close to auto oscillations, we see some apparent increase of the dissipation. This is due to the fold-over effects that we see in experiment. We can also very fairly simulate in our theoretical model. Now, this behaves totally normally. Now, what will happen if we go to the 3-magnon regime? So we apply a magnetic field either on the characteristic field or slightly to the side, so basically somewhere close. We see again that in the damping regime, the dissipation decreases with the incoming spin current. Okay, so here it behaves more or less linearly. However, when you go to the regime where the anti-damping torque becomes more strong, the dissipation just, well, seems to diverge. So we see here we see here an inversion of the spin torque effect. So you send an anti-damping spin torque into the system, and instead the dissipation just skyrockets. Okay, so why is that? Let us try to understand. Well, as I mentioned to you, the intrinsic nonlinearities are rather secondary, so let's throw them away and keep only the 3-magnon process as the nonlinearity of our system. In this limiting case, we can actually set up an analytical expression for the dissipation rate. So the effective dissipation rate of a magnon mode will be equal to the intrinsic damping of this mode plus a nonlinear contribution. And this nonlinear contribution has something to do with the 3-magnon process. You see here this psi. The psi basically says the coupling between the magnon modes, right? So this is the strength of the magnon coupling. Now, this Lorentzian is coming from the 3-magnon scattering. This is what affects the system. Now, if you send now a spin current into the system, what you will do is that you will affect the intrinsic damping of the magnon modes, but you will affect not only the damping of the lowest energy mode, but also of the higher order spin wave modes as well, right? So if you send a spin current anti-damping torque, it acts on all magnon modes. Now, for this Lorentzian, you can see the Lorentzian is given by the detuning frequency. So we have here omega. This is the frequency at which you are measuring the magnon mode. And omega n, this is the frequency of the higher order mode. So that means if you are on the 3-magnon scattering or very close to it, then the frequency of the magnon mode you're measuring is half of this frequency. So that means this term here goes to 0. Okay, so this Lorentzian, we're basically at the middle of the Lorentzian. Now this Lorentzian has also a quality factor, and this quality factor is given by the intrinsic damping of the higher order mode. So that means if we send an anti-damping spin torque, we make this smaller, we make this smaller, and then if this here goes to 0, you see that this whole Lorentzian basically boils down to psi square divided by alpha n. And if alpha n goes to 0, then this term here, this Lorentzian, basically starts to dominate. And this is exactly what happens, right? So you send an anti-damping spin torque. First, the decrease of alpha 0 is important. However, here at some point, this term starts to take over. Okay, so most importantly, what we see here and what we now understand is that because of the coupling of different spin wave modes, the intrinsic damping of the higher order mode plays the dominant role in the dissipation of the lower order mode. Okay, and this leads to an inversion of the spin torque effect. And well, I believe that this most likely will have far-reaching implications for the spin torque memory and spin torque oscillators applications. It may affect the switching behavior and auto-oscillatory behavior, may affect the energy efficiency and functionality. But I would like to say that this nonlinearity that is intrinsically present in nanomagnets is not just a nuisance, but also bears a potential for the emerging technologies. So, for example, if you think about the magnetic neural networks, so such this was shown by the group of Julie Grolier, for example, and he and Johan Ackermann, where two spin torque oscillators are communicating through spin wave modes. Well, in the neuromorphic systems, the nonlinear response of the magnetic neuron, which most likely is going to be a nanomagnet, is essential. And this is exactly what we are talking about, right? So this three-magnon process being the dominant dissipation channel is most likely the dominant nonlinearity. So what we need to do is we need to learn how to control this nonlinearity in order to make it useful for this emerging applications, emerging technologies. The same also for the field of quantum magnons and hybrid quantum systems. So just to mention it very briefly, the research goes more towards trying to utilize magnon modes as constituents of quantum information systems. And currently people are working more on coupling the magnon modes with other quantum coherent modes, for example, the cavity modes or qubits. But one can also think about coupling various different magnon modes to each other. And indeed, the nonlinearity that I have shown to you on previous slides is coherent. So we can couple magnon modes coherently and think about possible applications for the quantum information system. So bottom line is, now after we start to understand how the nonlinearity in this nanosystem works, we need to think about how to control it, how to basically tame it for the technologies. Okay, so this brings me to the second part of my talk. And well, if we think about how to control magnon processes, we need to look a little bit at the theory. So just very, very briefly, again, the magnon processes, of course, you can control through controlling the magnon spectrum, right? So you can design a magnet such that you, for example, create different splitting between the modes. You can apply different magnetic fields, so you can go closer towards the three-magnon process, farther away, etc. But these are all external parameters. The question is now, how do we still control the parameter that determines intrinsically the nonlinearity? And this is the coupling between the modes. Okay, so let me, this is a rather heavy theoretical approach, and I can only briefly sketch it for you. So what we do is we write the total magnetic energy of the system that includes the Zeeman interaction, exchange, and the dipole, and we write it down such that we use the effective amplitudes of the magnon modes, where we also involve the spatial distribution of the spin excitation. So we use the spatial profiles of the magnon modes. And then when we write it down, we can look at the different terms that occur, and we can look at the symmetry of these terms that correspond to the three-magnon regime or three-magnon process. What we will find is that the dipole interaction indeed is the dominant coupling term. So the magnons are mostly coupled by the dipole interaction. And very interestingly, we find that in the most straightforward case, so basically for an ideal case, most of the three-magnon processes should actually be forbidden by symmetry. They actually should not occur at all. However, we find an experiment, and we have measured hundreds and hundreds of nanoscale devices, hundreds and hundreds of magnetic tunnel junctions. We find that these magnon processes are extremely abundant in experiment. So here I'm citing our work that is based on theoretical efforts of Roman Verba, Graham Rowlands, and Vasily Perkevich. It is possible to write the magnon coupling as this overlap integral, as this convolution that will contain several parts. So first you will have here the spatial distribution of the spin excitation. So these are basically the magnon mode profiles that are involved in the process. You will have mu, this is the static magnetization. And you will have this kernel n that basically corresponds to the dipole interaction. So now from there is, of course, this disparity between the theory and experiment. The theory says that most of the processes should be forbidden in experiment, yet we do see them. However, we can use this already as an idea of why this is the case. So if we look here, you can circumvent, or you can basically increase the coupling between the magnets either by doing something with the static magnetization of the magnet, or by doing something to the mode profile of the magnon mode itself. So you basically see two paths. For the simplest case of an elliptical magnet, these are the ones that we typically work with. The simplest approach would be to create a broken symmetry micromagnetic state. So you would just apply a magnetic field, which is at an angle to the symmetry axis of the magnet. So you would turn the magnetization a little bit away from the symmetry axis. Now, however, I can imagine that this approach, and we have tested this in experiment, this works, may not be very favorable for applications, because this may shift the magnon modes in energy too much. More elegant approach that we have chosen to work with would be to work with the broken symmetry magnon states. So we do not want to affect the magnon spectrum too much. We don't want to shift it. We don't want to apply large external magnetic fields, but we would like to change the actual symmetry of the magnon mode itself. However, if you think about it, because we are working with nanomagnets on the lateral scales of a few tens of nanometers, maybe 100 nanometers, in order to change the symmetry of such a mode, you would need a field, symmetry breaking magnetic field, that would show a non-uniformity on the same length scale as the magnon mode, as the nanomagnet itself. So if you need a magnetic field with non-uniformity in this length scale of few tens of nanometers, you need a source of this magnetic field to be nanoscale itself. And luckily, in our devices, we are very happy to have such a source. So if you look at the typical magnetic tunnel junction, so this is the free layer, this is our zero-dimensional magnet that we are working with, that we are looking at, and then we have the synthetic antiferromagnet underneath. Now, this particular device has in-plane magnetization, so it has rather weak perpendicular magnetic anisotropy. So this is the easy axis, so it's just horizontal here on this page. Now, if you apply magnetic field along the easy axis of this device, well, the synthetic antiferromagnet first will not respond to the magnetic field at all, right? It will remain antiferromagnetically coupled to each other. And the order of the magnetization will be parallel to the external field or antiparallel. However, if you apply sufficiently large magnetic field, the synthetic antiferromagnet will undergo the spin-flop transition. So the magnetization will basically flip and align itself almost 90 degrees to the external magnetic field. So what we can do is we can use this underlying synthetic antiferromagnetic, because it is small, it is nanoscale, as a source of a stray field. So I'm going to show you these stray fields in this normal state and in this spin flop state. But the bottom line is we have now a nanoscale source of magnetic field from which we hope to get a magnetic field with non-uniformity at the nanoscale. So we can actually see the spin flop in the typical measurement of the resistance of this device. So this is the magnetotransport of a single MTJ. So if you apply negative magnetic field, what happens is that the free layer just follows the external magnetic field. It aligns itself to the left. The synthetic antiferromagnet is as shown in its normal state, right? So because of this, the resistance is high, given by the tunneling magnetic resistance, right? Antiparallel state. Close to the zero field, you have the typical transition. The free layer basically switches from left to right, back and forth, so everything's normal. Now, if you increase magnetic field, so you arrive here at the parallel state. Okay, so the magnetization of the free layer and the top SAF are parallel to each other. The resistance is low. However, if you then apply more magnetic field, the spin flop transition happens, and the magnetization of the SAF layers basically rotates at approximately 90 degrees towards the external magnetic field, while the free layer continues to remain parallel to the external magnetic field. So you arrive at this intermediate resistance state. Now, very importantly here, so if you go from left to the right, you will have this spin flop transition. If you go left, the spin flop transition, the spin flop state basically flips back to the normal state. So what we see here is the hysteretic behavior, where we can flip the SAF into the normal state, into the SAF, and we can achieve magnetic fields for which we can have either one state or another state, depending on what we do with the magnetic field. Do we go from left to right or from right to left? Okay, so now in the parallel state, so in this state here, we have done micromagnetic simulations of the device that we worked on. So we have here, this is the static magnetization of the free layer, this is CCF top, this is CCF bottom, and you see everything is nice and neat. So these two are anti-parallel, these two are parallel to each other. The magnetization is actually mostly uniform, so we didn't see much of the deviation from the orientation of magnetization at the edges. So what we can do here is we can calculate the stray field that comes from the bottom two layers and calculate this value and magnitude of the stray field at the position of the free layer, right? This is where the physics happens. And this is shown here. So what you see here, yes, the stray field shows some small amount of non-uniformity, and this field is...
Are we going to or? Yeah, let's finish.
Oh, okay. So this field is rather small, and it does not affect the magnetization of the free layer of the free layer. Okay. Now, if we go into the spin flop state, so if we flip the magnetizations of the SAF layers to be, you see here, mostly 90 degrees towards the external magnetic field. Then we have a rather strong stray field coming from these two layers at the position of the free layer. So it is order of magnitude larger, and this is more non-uniform. However, this is very important, this stray field here does not affect the static magnetization of the free layer. So this is much larger, and yet this is not large enough to actually turn magnetization too far away from this original state. Okay, so this is exactly what we want. What we have now created a switchable stray field, right? So we can switch the stray field from being small to rather large and very strongly non-uniform. But on the other hand, it is small enough not to affect the static magnetization. This is exactly what we wanted. Okay, so we have now this controllable dipole switch to toggle the nanoscale field or magnetic field with nanoscale non-uniformity. Okay, so now let us take a look what the magnon spectra of this device look like and how they are affected by the switching of the SAF from the normal state into the SF state. So we have here the antiparallel state, spin flop state. So we change here the magnetic field from left to the right. If we increase the magnetic field, at some point, the device basically just switches into the spin flop state. And what you see here is that if we look at the lowest energy mode, then the energy of this lowest energy mode is actually not affected by the SAF going into the spin flop state, which basically says that the magnetic field itself is rather small. So the contribution to the anisotropy by the Zeeman term is actually very small. However, if you go to the higher order modes, you will actually see that some of them change in frequency rather drastically. And this is exactly what we actually wanted to do, right? So we wanted the magnetic field to be small. We wanted the magnon gap not to change, but we wanted it to couple to at least some of the magnon modes and affect them. Okay, so if you go with the magnetic field from right to left, so you start from the spin flop state, and the spin flop state persists for longer time because the spin flop in our SAF is hysteretic, right? So if you go from left to right or from right to left, you can, for the same magnetic field, you can be either in the parallel state or the spin flop state, depending on the history of what you do with the device. Now, importantly, again, we run here micromagnetic simulations. So these are the spin wave modes for this particular system. So we just call the modes here 1, 2, 3, etc., etc. These are the profiles. And we will find that in this field range that is interesting for us, we can have two different 3-magnon processes. We can have a process where the mode number 1 and the mode number 4 interact, and we can have a process here where mode number 1 and mode number 5 interact. And if you go from right to left, you will be in the spin flop state in the magnetic field, which is very similar, and you can still have this very same magnon processes. Okay, so if we are in the parallel state and we look at the dissipation of the lowest energy mode as a function of frequency, we actually will find that it behaves, well, nearly Gilbert-like, right? So there is nothing. So these two arrows here indicate the frequencies of the magnetic fields where in principle this nonlinearity should occur. And yet we do not see anything. We do not detect any magnon processes. What does it mean? Although the energy conservation would be fulfilled here and here, the nonlinearity does not take place. And this is because, indeed, these processes are forbidden by symmetry. And the stray field and the, let's say, surface effect or edge effects, right? So this non-uniformities, defects, whatever, in the free layer are just too small to make this nonlinearity occur. Okay, so we have indeed a case where these two processes are very small, or basically maybe even zero, because they're forbidden by symmetry. Okay. Now, if we go to the spin flop state, right, and we go to magnetic fields and frequencies which are very similar to this one here, we can find these very same processes where the mode number 1 and mode number 4 and mode number 1 and 5 interact with each other. And we see here then indeed there where this magnon processes should occur, we have a strong resonant enhancement of the dissipation. Okay, so we see here this huge enhancement of the dissipation, two very distinct dissipative states. So indeed, this stray field that we have created from the stray field of the SAF indeed has broken the symmetry of the magnons and has enhanced the magnon interaction. Okay, just to make sure that in the parallel state, the three magnon process is indeed there, that we are not missing something, what we can do is we can send in an anti-damping spin torque. And this, you remember at the beginning of my talk, I told you that if you send an anti-damping spin torque, the nonlinearity at some point starts to overtake and actually the dissipation increases. And this is indeed what happens. So we send an anti-damping spin torque. So this is the current, even the current increases. And then here at zero current, at zero spin current, there is no nonlinearity. However, at some point, this nonlinearity starts to become pronounced. So it is indeed there, but the magnon interaction is small, right? Okay, what we can do now in the spin flop state, where we already start with a rather large nonlinear contribution to the dissipation, is we can perform a power dependence. So we can decrease the power sent through the device, the microwave power sent through the device. We can decrease the excitation amplitude. And by doing so, we can decrease the contribution, the nonlinear contribution, and we can arrive basically here at something that looks more or less like Gilbert damping. Again, this measurement is rather complicated because you need to use very, very small excitation powers and you barely see a signal. Okay, so we see here indeed the three magnon scattering is very strong and it decreases with decreasing power as expected, as we have calculated for previously in our theoretical model. So we can use this measurement in order to calibrate the magnon interaction. So we cannot measure an absolute value of this magnon interaction, but we can compare magnon interaction in the spin flop state and in the parallel state. And this calibration shows us indeed that in the spin flop state, so when you have this presence of the non-uniform magnetic field, the magnon coupling between the mode 1 and 4 and 1 and 5 is indeed more than one order of magnitude larger than when you have no stray field acting onto the free layer. Okay, so this basically proves that yes, indeed, you can use stray fields, or you can use magnetic fields with nanoscale non-uniformity in order to change the actual interaction, the actual coupling between the modes, and this can be done rather effectively. So at least one order of magnitude, probably even more. Okay, so this brings me to probably two last slides of my talk, because I'm already running out of time, and this is what I'm going to do here is I'm going to show, well, how many different magnon processes can you actually have a nano device? Well, I mean, you can think of the higher and higher and higher order. So what do we need to do? Do we have to work our way through all of them now? I mean, does it end anyone? You know, so what do we have to do? All right, so let me just very briefly sketch what is going to happen. So we have here another device, and you can see there is already, well, many nonlinearities present here. But what we can do here, if you look, we definitely can find a 4-magnon process. So here, 3 magnons of this lower order mode go into 1 magnon of the higher order mode. So before we had 3 to 1, 2 to 1, now we have 3 to 1. Okay, this is still a degenerate process, degenerate 4-magnon process. Okay, we also do the analytical theory, we do the calculations. I just want to cut the story short. Bottom line is you again will get a Lorentzian type contribution to the dissipation. So you will get again an enhancement of the dissipation, and you will get a nonlinear frequency shift. And again, both of them will have a Lorentzian shape. The Lorentzian will be in the detuning of the frequency. So again, you just need to find wherever these frequencies cross, okay? And there will be the quality factor, and the quality factor again is the damping of the higher order mode. So the behavior is basically very similar. Here we have a proof of principle measurement where you again send anti-damping spin torque into the system, and you can see with increasing anti-damping torque, the resonance, the dissipation actually increases. So very similar to the 3-magnet process. However, the 4-magnet process plays a less dominant role because you see here it's a higher order effect. Okay, just to show you how much more complicated it can get. So this is another device. Okay, and this is not just because we have chosen the most complicated device. This is because these devices come from industrial collaborators. These are devices that are indeed important for the technologies. And you see it can become even more and more complicated. So if you just measure the dissipation of such a device, it's a huge mess. But we actually are right now at the point where we start to understand all these Lorentzian contributions, so these multiple Lorentzian contributions to the dissipation. And based on the hundreds of devices that we have measured so far, I just want to summarize this. The most dominant nonlinearities that we observed so far, the number one is the degenerate 3-magnon process. This is the one that I explained to you at the beginning of my talk. So this was the first half of my talk. Then the second one is probably the degenerate 4-magnon process. And there is also non-degenerate 3-magnon process. This is basically where instead of just 2 modes interacting with each other, 3 modes are interacting with each other. Of course, higher order processes are present in the system as well, but because the magnitude decreases with the higher order, I think that these are the ones that are probably most interesting in terms of phenomena that can be observed from the fundamental point of view, but also from the technological point of view. Okay, with this, let me please summarize. So we have worked on disentangling dissipation processes in 0-dimensional magnets. We find that the nonlinearity is constituted by resonant magnet processes. We find very importantly that resonant magnet processes redefine the spin torque response of the nanomagnets. So most importantly, they basically can invert the response of the spin torque to the spin torque. We found a way we discussed and found a way how to engineer magnet interaction via nanoscale fields, and we have shown a proof of concept. And as an outlook for applications and technologies, I think that this understanding of the dissipation that we have gained may be very helpful for improving the performance and designing spin torque devices, like, for example, spin torque memory. It is basically just most best suited, I would say, for tuning the nonlinear response of magnetic neurons in neuromorphic computing. And as an idea, we think it may be important for entangling magnon states for the quantum magnonics, for the emergent field of, for example, hybrid quantum systems. With this, I would like to acknowledge my collaborators. This is the group of Ilya Krivorotov, Roman Verba, Vasil Tiberkevich, Boris Ivanov. I would like to acknowledge the funding by NSF. These are the 2 references for you if you're interested, I hope. And thank you very much for your attention.
Okay, sorry, I was a technical difficulty. I couldn't unmute myself. Thank you very much for the interesting talk. And you can thank the speaker using a reactions buttons. So this talk is open for questions. If you have any questions on Zoom, please use raise hand function. And if you're watching this on Twitch, you can type your questions in the chat box. Any question? Let me ask the first one. If I understand this correctly, the 3-magnon process is intrinsically a nonlinear process. But if you create some local non-uniformity, so that is with a strong stray field, you can significantly lower the threshold of the excitation. But I also remember you saying that for the 3-magnon process that you're talking about, there is 0 threshold. You're always going to have that.
Yes.
So so does that mean that even if I just uniformly exciting this lower frequency magnon, that double the frequency of the mode will occur even if I excite a very low energy?
Yes. So the 3-magnon process is always present. There is no threshold. So there's absolutely no threshold. The increase of the magnitude of the 3-magnon scattering as a function of power is absolutely continuous. I don't remember exactly right now the order. It's a polynomial of approximately x to the 4 or something like this. But it is present even at low excitations. Now, the fascinating point indeed is that if you just look at the perfect nanomagnet, you will find that most of the 3-magnon processes should be forbidden by symmetry. However, in experiment, in 90% of the cases, they are there, which means, and this idea came up actually in a discussion with Eric Fullerton, is that first, of course, you have in any real device some kind of non-uniformities, defects, for example, some edge roughness or something like this, right? So this is of course one possibility, but also for mostly for the MTJs, you have the underlying synthetic antiferromagnet. The underlying synthetic antiferromagnet is designed such as to minimize the stray fields. Nonetheless, they are still there. So in particular in MTJs, this is my hypothesis, the 3-magnon scatterings are particularly strong just because of this non-uniform stray fields. Of course, you can use now this synthetic antiferromagnet, so once we understand where it comes from, in order to create a very particular, stronger non-uniform magnetic field or magnetic field. It may not necessarily be strong, but has a very particular symmetry to particularly couple particular modes that you may be interested in.
I see. Yeah, thank you very much for the explanation. Do we have other questions from the audience? I want to ask another question regarding the actual measurement technique. The spin torque ferromagnetic resonance, you have a citation there from a paper, I think it's 2012. But how exactly is this conducted? You apply an AC current and measure rectification, or you just apply DC to measure the oscillator effect, the emitting microwave?
So in the spin torque ferromagnetic resonance, you send a microwave current through the multi-layer stack. The microwave current by means of Ørsted fields and also spin torques, AC spin torques, excites the magnetization. This leads to resistance oscillations.
Right.
Resistance oscillations happen at the same frequency as the microwave current. Because of this, you have the rectification effect and you measure the DC voltage. The DC voltage can be measured using the lock-in amplifier if you use an additional modulation technique. In our case, we use field modulation because it has proven to give us basically the best accuracy, the best quality of the measurement.
I see. Then, but in some of the graphs, you have the x-axis as DC current to apply. So that is on top of microcurrent, you also apply a DC current to modulate the damping?
Yes, not quite. So the DC current that you can send in addition through the device will lead to a DC spin torque, DC spin current that will affect the damping. If you do so, you will have, in addition to the rectification, also the so-called photoresistance contribution to the signal, but it can be all, disentangled, fitted out. Nonetheless, in addition to this, you still have external modulation of the magnetic field that basically leads to the modulation of the signal.
I see. So if you're using rectification, using oscillation of the resistance, shouldn't the two configurations, magnetization configuration, be non-collinear?
We apply magnetic field and also the modulation along the easy axis of the device. So this doesn't change the mutual orientation of the layers. So everything is parallel. Everything is.
I'm thinking if it's parallel and it starts precess, the resistance should be twice the frequency, right? Not the.
Oh yes, yes. Yeah, of course. This is a very good point. So if you look at the photoresistance and rectification signal and photoresistance, in the easy axis you will actually have only the photoresistance. However, there are additional rectification effects that lead to the signal. It's a very good point. I would say it is not fully understood. So in my personal opinion, working or speaking about the amplitude, the absolute amplitude of the signal in the easy axis is still a little bit difficult. But because we are mostly concerned here, not with the magnitude of the signal itself, but with the line width, this problem does not affect us too much.
I see. Yeah, thank you. Do you have any other question? If you're on Twitch, you can always type your questions in the chat box. I can read it for you. I got some response from Twitch, but I don't know whether the person is still typing or not. We'll give another 10 seconds. If I don't see a question, then I guess there's no more question from Twitch then. Okay, I guess there's not many questions there. All right, any question from Zoom? If not, I want to thank Professor Barsukov for this very interesting talk again.